Okay, I think Stefan, please, the stage is yours. And, you have around 45 minutes, and I guess we will wait until the end to ask questions. Okay.
Well, thanks a lot, Titu, for organizing the seminar and introducing me. So what I'm going to speak about here is about improving quantum chemical simulations while addressing key open challenges in DFT. Okay, so nowadays lots of chemistry research, it takes place at a computer, and for accurate treatment of different treatments, we need to consider different scales. And when we speak of chemistry, what governs chemical principles is the motion of electrons, and for that we need to rely on quantum mechanics. And when we speak of quantum mechanics, nowadays more than 90% of quantum chemical calculations are based on density functional theory, or DFT. This percentage, it is even higher in solid state physics, where more than 95% of quantum mechanical calculations are done by DFT. And one interesting fact is that based on estimates of NVIDIA, around 1/6 of the world's supercomputing power is devoted to DFT calculations. So it is really a huge thing. And so here I list several recent successes of DFT in terms of its bona fide predictions. For example, new better catalyst for the Haber-Bosch process was predicted by DFT. DFT is used as a very important tool in materials genome project. Also, world's hottest superconductor. It was first predicted by the DFT calculations, and then it was made. And DFT has also helped in designing material that enabled removing lead from MacBook Air. And in addition to these successes, there are lots of failures in DFT that are traced back to well-known deficiencies. For example, in the chemistry of transition metals, the DFT failures are very, very common. And on the other hand, for main group chemistry, DFT is nowadays very close to converging towards the desired chemical accuracy, but still there are cases where DFT can fail even in the domain of main group chemistry. And okay, so I list here successes and open issues in DFT, and I ask here where I am in this story. So the main goal of my research is to expand the applicability of quantum chemical simulations by addressing some of the key unsolved problems in DFT. So these unsolved problems include strong electronic correlations. That's highly relevant for a range of chemical domains, such as transition metal, homogeneous catalysis, metalloenzymes. I also work on making DFT better, working for non-covalent interactions. So since typical DFT methods, they do miss long-range interactions. And I work on the so-called density-driven errors, which are highly important for things like barrier heights, potential energy surfaces, and so on. Okay, so my work on the strong electronic correlations and long-range interactions, that was mostly done during my PhD, whereas some more recent work on long-range interactions and these density-driven errors, I've done these mostly during my postdoc with Kieran Burke at UCI. And yes, my PhD I did with Professor Paula Gori-Georgi in the Netherlands, in Amsterdam. Okay, so here I'm going to give you a short overview about each of these topics. So I'll start with these density-driven errors. Okay, so I'll quickly review how DFT, at least in principle, works, and it's important to remember that at least in principle, DFT is exact theory, and how it roughly works. You start with nuclear coordinates, you find the exact density for these specific nuclear coordinates, and then you apply the exact functional to this density, and this in principle enables you to obtain the full description of quantum nature of matter. And how DFT works in practice, there are thousands of approximations. Sometimes they work, sometimes they don't. And so when we run a practical DFT calculation, we again start from nuclear coordinates, we obtain the approximate density, and then we apply an approximate functional to that approximate density, and we get, in contrast to what DFT is in principle with approximations, we have situations where sometimes they work, sometimes they don't. And the total error made by DFT, we can write as the difference between the exact energy and the approximate energy. And okay, so here, from what we can see, the problem is compounded because in the error, we actually have two contributions, one coming from the approximate energy, and the approximate density. And what I was recently doing, I was working on the so-called density functional analysis, where we tried to make where we try to disentangle these two sources of error. And basically, since they are both types of error, we have two approximate things here. One is the approximate functional and the other is approximate density. So in principle, we here partition the total error into the functional error and the density error. And okay, so we can define the functional error if we rewrite here, what is this, the first equation, if we rewrite it with the exact density. And in this way, we completely eliminate the density error and only stay with the functional error. And then, okay, what's going to be here? The density error, it's going to be just the difference between the total error and the functional error. And okay, so from this, we can see that the error in DFT we can separate into functional error, which is typically much bigger than the other density-driven error. And okay, what is the practical implication of this? So density error, they can be greatly reduced by methods that are called density-corrected DFT or DC-DFT that I was recently working on. Okay, so here I show one practical, here I show one example. This is the dissociation of sodium chloride. If I apply here as an exchange correlation function, if I apply TPSS, I can see that it's working well around the equilibrium, but then as you stretch the bond, it starts failing. But however, if I apply again the same functional, but using on the exact density, I can see that my error is greatly reduced once I stretch the bond, meaning that in the dissociation limit, the total error of DFT is mostly governed by the density. And okay, so, but in practice, of course, we cannot calculate the exact density. So is there a way around this? Okay, so how we can reduce these density-driven errors? First, we need to have some indicator that raises a red flag as soon as we encounter big density-driven errors. And okay, in practice, in principle, that would be the best if we can always evaluate what is the total density-driven error, but we don't have access to the exact density. That would cost a lot. So in practice, we define this sensitivity criterion, which is the difference For a given functional, we evaluated on the Hartree-Fock densities that are most of the times over-localized, and on the LDA densities that are most of the times delocalized. And as soon, so this serves as our proxy for density-driven errors, and as soon as it is above 2 kcal per mole, it's advisable to use Hartree-Fock densities instead of the self-consistent ones when we want to apply certain density functional. But here, this is a very important thing. Okay, so lots of people say, okay, Hartree-Fock densities, they are much worse than the DFT ones. But here, what is very important to know that this is only useful when this red flag is raised. In the other words, when the DFT densities are even qualitatively bad. So, and okay, so coming back to my previous example, I plot here this S, and I can see that it increases as we stretch the bond, and as the bond and roughly beyond 3 angstrom, basically DFT functionals, they are crying out for better densities, and as soon as we apply better density, Hartree-Fock is in this case good enough because it is free of self-interaction error, and it is indeed better in these specific cases when DFT fails, where DFT densities fail even qualitatively. Okay, so this has great implications, for example, for potential energy surfaces. So for example, so I show here for this SN2 reaction, I show here on the left-hand side, I show here the accurate potential energy surface as we go from product to the transition state. And in the middle, I show the error of the self-consistent DFT. And now I look at my plot of the density sensitivity, where whenever it is greater than 2 kcal per mole, this suggests that there are great density-driven errors, especially around in this upper right corner, when we are around the transition state. And as soon as we apply the same DFT to Hartree-Fock densities, we can see that, we can see here that the errors are greatly reduced, especially in this region around the transition state. Okay, so this has very important implications for finding the transition state. Okay, so here this is the accurate plot for the transition state where the saddle point is identified. But if we look at just DFT here with the PB functional, it basically, okay, here this whole area is blue, meaning that it fails to locate transition state, and it predicts that the whole process has no barrier. But as soon as we correct the density by means of the Hartree-Fock, we again are able to go from blue to red, meaning that the barrier is found, and the transition state, okay, its position is not perfect, but it's still way better than what we have in the middle. And recently we applied this idea also to double hybrid functionals, where we developed the so-called BL1P. It contains one parameter, and it has been trained on the Hartree-Fock densities, and it is specifically designed to work for systems that suffer from big density-driven errors, such as sodium chloride. So this is the case where standard double hybrids fail very badly, but this BL1P is doing very well. At the same time, this BL1P, it is accurate for systems that are sensitive to density-driven errors, but at the same time, it is highly accurate across chemistry. So even though it is trained, even though it contains only one empirical parameter. So here in this plot, I show various functionals, their errors for a wide variety of chemical systems, mostly data sets of DREAME. And basically from what we can see here, that this BL1P, even though it contains only one empirical parameter, it is highly competitive with more highly parameterized functionals, and at the same time it does well where the other functionals do not. One example for this is like the so-called delocalization error, which is present, for example, in Diels-Alder reaction energies. And this is the case where standard DFT functionals, even double hybrids, such as B2-Blip, they greatly overestimate energies of Diels-Alder reactions, whereas we can see that this BL1P, this newly developed double hybrid, greatly improves the energies of these reactions, as can be seen on this parity plot. Okay, so this would be it about density-driven errors. So now I'm going to talk a little bit about strong electronic correlations. And strong electronic correlations, okay, so we have lots of density functional, and what they have very common is that basically almost all of them fail for strong electronic correlations because, okay, so we need to remember that DFT is in principle the exact theory, and strong correlation, they arise when the physics of the system, the physics of our system of interest is disrupted by where strong correlation actually disrupts the non-interacting physics of the underlying Kohn-Sham system in density functional theory. And it is very difficult for standard approximations to connect the non-interacting system with the physical one when the strong correlation is present. And that is the main reason why a variety of density functional approximations fail for strong correlation. And so why this is important? Because strong correlation, it is present in bond breaking, it is omnipresent in the chemistry of transition metals, functional materials, metalloenzymes, and the inability of DFT to capture strong correlation, it hampers its overall predictivity and reliability. And what is interesting for all these approximations, even though there are thousands of them, they are all based on the same paradigm. It is called the Jacob's ladder, formulated by John Perdue, where one starts from the density, goes to its gradient, orbitals, occupied orbitals and empty orbitals, and one is supposed to reach the heaven as you go to the higher rungs of this ladder. This is indeed true for systems that have no strong correlation. So as said earlier, current DFT are doing very good for systems that are weakly correlated, but all this approach has been proven to be not very successful when applied to strong correlation. Okay, so over the recent years, I was working on developing a new framework for the strong correlation. It departs entirely from this Jacob's ladder. And instead of using these ingredients, the ingredients of this new framework is based on the exact theory of strong electronic correlations. And instead of using the density gradient, the Laplacian of the density, it uses fully non-local terms, which are incorporated by the integrals of the density, which appear as the main structural motifs of the exact mathematics of strong electronic correlation in DFT. And okay, so here I go a little bit into mathematics. I will show here formulas, but I will not go so much into mathematical details. So this is the so-called multiple radii functional that is based on this framework. And what I show here as the key ingredients are, what are its key ingredients are the integrals of the density that encode highly non-local correlation, and it enables a reference selection to see the positions of other electrons in the system. So this function is fully non-local in the sense that a reference selection at a given spatial position basically knows everything about the other electrons in the system. Okay, so how, even though the mathematics of this functional is rather simple, okay, it models the so-called exchange correlation energy densities. And it, okay, so here I show the density of beryllium. And I label my reference electron is a tar, and I want to find the position of other electrons present in the system. So the positions of other electrons present in the system I modeled by Dirac delta function. Okay, we know that this is nothing like the real wave function, but here it serves only as the auxiliary object to build the exchange correlation energy densities. And I start integrating. Okay, so I say, okay, there should be space around one electron in between my reference electron and the second electron present in the system. And then I continue integrating, find one more, and then I continue doing that, and I find the last electron. And this is what I repeat for each point in space. And this procedure is inherited from the exact mathematics of strong electronic correlations. And these integrals of the density, as said, they encode highly non-local information telling us about where the other electrons are. Okay, so even though this method, so again, multiple radii functional of MRF, even though it is remarkably simple and it roughly comes at the cost of hybrid functionals, it has a range of advantages that are missed by standard GGA and meta GGA functionals. For example, it is free of self-interaction error. It captures accurately low density limit. It is, by construction, it is able to capture the physics of open shell bond breaking. It also comes at a relatively low cost, roughly that of standard hybrid functionals. And it also provides highly accurate exchange correlation energy densities. Okay, this can be shown here for atoms. The green ones are obtained by the MRF. So even though I show, okay, we know that atoms, they're typically not very challenging in the sense that they are weakly correlated, but we need to have in mind that this MRF is basically a brand new functional. So we need to make sure that it does well in cases where the standard DFT already is very successful, such as atoms. So here we can see that these green curves, they're in very, so here this is shown for neon and H minus, they're in a very good agreement with the reference energy densities. But of course, the primary goal here is not to treat weak correlation. So what we are interested in is like the treatment of strong correlation. And here I show the results for the hydrogen molecule. So we know as we stretch the bond of any open shell system, then the standard DFT basically fails. The error becomes large due to strong spatial correlations between electrons. This can be fixed, for example, if one artificially breaks the spin symmetry of the system. And so, but here we can see that our method, so-called MRF, does it well without a need like to artificially break the symmetry of the system. And okay, so here I also look at the correlation energy densities for us along the internuclear axis. When H2 is stretched, I can see that MRF delivers the accuracy basically the same as exact full CIs used here, whereas the standard DFT, they are by roughly 3 times worse. Okay, so this was it about strong correlations, and I will also speak briefly about long-range interactions that are important for capturing the physics of non-covalent interactions. And what I would like to remark here is that for non-covalent interactions, I basically use the same formalism as for strong correlation, but what I add here as an additional ingredient is the second order perturbation theory, and I explain that later. Okay, so first I add here second order perturbation theory, and okay, what is my motivation for doing that? Okay, until recently, second order perturbation theory, specifically MP2, it was considered a relatively safe choice for treating non-covalent interactions, and certain failures of MP2 in non-covalent interactions, such as those in stacking complexes, they have been considered accidental. But in a recent work of Philip Furke, it has been shown that many body perturbation theory, the MP series actually diverges as we go to larger and larger molecules. So this makes MP2 basically qualitatively unsuitable for the description of non-covalent systems. Okay, this is not only the problem of MP2, because lots of other methods such as MP2.5, double hybrids, they use MP2 in their scheme, and they because of that they inherit lots of shortcomings of MP2. And okay, so failures of MP2 are also seen in a L7 dataset, which combines 7 large non-covalent complexes, where we can see that depending on a complex, the errors can range up to the relative errors in binding energies can range more than 100%. And okay, as we go to one order higher, from MP2 to MP3, we do reduce the error at a much greater computational cost, but we can see here that the errors are still huge. They range up to 80%, meaning that this is not the problem of the MP2, but also about the problem of the whole divergent MP series. And okay, so how I have recently approached that, I have used the adiabatic connection formalism. Specifically here, this is the Moller-Placet adiabatic connection, where I connect the non-interacting system, here this would be the Hartree-Fock system, with the physical one, in such a way that the slope of the adiabatic connection integrand is given by the Moller-Placet expansion. And okay, so basically, if I look at the integrand, this correlation energy is going to be as the integrand over this W lambda, which is the integrand connecting the Hartree-Fock system with the physical system. And okay, so one can ask, this integrand here is the exact one in this cartoon is shown by this black line, and the MP2 one is shown by the dashed blue curve. And one can immediately ask the question, oh, when do we expect MP2 to be accurate? Okay, the more the linear the exact curve is, the better agreement between the MP2 and the exact theory we can expect. But as soon as the exact integrand starts having some pronounced curvature, we would expect MP2 to fail. Okay, how we have approached this, we said, okay, let's, besides MP2, use another input quantity. And here this is going to be from the strong coupling limit. And in this way, we incorporate additional information and avoid bias towards weak expansion. And then how we obtain the, and okay, this strong coupling limit here, W infinity, shown by this pink line, we model it very simply as the integral over the Hartree-Fock density. And then what we construct a curve which does interpolation between the MP2 limit and this pink limit. An additional thing that is added here is the size consistency correction that comes at no additional cost, because it has been thought that this approach suffers from the size consistency issues, but we have shown recently that this can be easily fixed, and that once the size consistency error is removed, as shown here in the TOC, the errors are greatly reduced by an order of magnitude. And okay, so what we have here, I use the MP2 correlation energy and the exact exchange. These are my quantities that they obtain from an MP2 calculation. And what I use additionally is I obtain this integral over the Hartree-Fock density, and I then plug this into the formula that is shown here in the equation 1, and I applied the size consistency correction on the top of that. So these are the ingredients that I'm using, and what is very important here to know that all these things that are in pink, they come basically at no additional cost. I mean, they come at an eligible computational cost in addition to what's done by MP2 calculation. Okay, so here I show some results, and I define this quantity here as the difference between the exact correlation energy and that one predicted by MP2. So in fact, this is going to be the error of MP2. And I show here how the first method that we have constructed, the orange one, how well it corrects the MP2. Okay, if it matches the black line, it corrects MP2 perfectly. And we can see, okay, with it, we have reduced substantially the MP2 errors, roughly by 2/3. But still we are not perfect as the MP2 energy becomes large. Okay, so we wanted to consider, okay, what is a way to improve that? So far, we haven't chosen any empirical parameters, and we thought, okay, how we can improve it, so to get even better improvement over MP2, we need a more flexible interpolation form, and we have also added some empirical parameters which are here trained on the S22 data set, and here they're shown in pink. Okay, once this is done, we are doing much better. So this is SPL2, which are here the green dots, and we can see that it improves MP2 much better. So basically, even here, when the errors of MP2 are about 20 kilocal per mole, our model here is basically able to correct nearly the whole error of MP2. And okay, so here we are zooming on the situation around 0. Our previous method, in cases where MP2 errors were negative when it underbinds, our previous method, the orange one, it was correcting MP2 in a wrong direction, whereas these new ones, they are doing well and correct MP2 in a right direction, even in the cases where it underbinds. Okay, so here I also show some results for non-covalent data sets. Okay, so just please follow the green line. This is our method, and it's doing well here for noble gases. Here, this is an example for stacking complex where the MP2 is doing very bad, and we are giving here major improvement. Okay, so this is another complex. It's acetoamide. So it is more characterized by, it's bonded by hydrogen bonds. And in this case, we are still doing better, and also much better than the standard DFT once the D3 correction is applied. And what is important here, in terms of our method, it is accurate for non-covalent interactions, even without applying any D3 or D4 correction of green. Okay, so now I come back to our starting point, the L7 data set, where I show the average relative errors. And we can see here, the MP2 here basically beats all the other ones, including MP2, MP3, PBE with when Tkachenko-Scheffler correction is added, and its relative error is only 5%. So, okay, so this was it about my non-covalent interactions and my research lines in general. So what I'm going to talk about now is I'm going to give an overview of what are my future plans. Okay, so I was because the idea of this talk was like I wanted to apply for CNRS position, and if in case I get it, I wanted like to say here what I would like to do. Okay, so here I roughly divide my potential projects into 3 groups. Okay, so I say what are the topics. Strong correlation, here I have their van der Waals interactions and application of DFT to the surface science. And for each of those potential projects, I define what are the goals. For example, for strong correlation, it would be to what I showed you here, the new framework. The idea would be like to transform this new DFT framework into a mature computational approach that is able to work for very difficult system. In terms of non-covalent interactions, the goal would be like to obtain the accurate low-cost treatment of non-covalent interactions. And finally, in regards with applying DFT for surface science, the goal would be like to transform the applicability of DFT via developing tools analogous to the ones that I developed for molecules. And okay, so now I will elaborate on each of these topics. So starting for strong correlation, it is indeed a big problem in quantum chemistry. As noted here, 85 years after Schrodinger's equation, we solved half of the problems, and and strong correlation makes up the other half. Okay, so strong correlation, it can be accurately treated by wave function methods, such as when, for example, CAS-SCF is combined with CAS-P2, but this still comes at a great computational cost. And here my goal would be really to develop the pure DFT framework to be able to treat non-covalent interactions. And the relevance of this would be, it's important for homogeneous catalysis, for the chemistry of transition metals, lots of things like metal organic frameworks. As said, also strong correlation is also present in cases when the bonds are broken and form, and therefore this is also highly relevant for reactivity in general. Okay, in terms of collaborations, I believe that method development group from TEL can greatly benefit from this, also from the SEM group. I think what this is done for strong correlation is highly relevant for transition metals, open shell configurations. Sorry, one sec. And also I believe that quantum package that is developed in your lab can also greatly benefit from that, because all these methods, these specific DFT methods and other ones, they can be developed into, they can be implemented into quantum package. Okay, so non-covalent interactions, the primary along these lines, a specific goal would be like to build the infrastructure to transform the highly promising result into practical methods that can be used for simulation of large systems. And for this one, I think like there are plenty of collaborations with interstellar chemistry. Okay, so here I show like integration of these two research lines and what are the ultimate goals. For example, for strong correlation, what this is relevant for the chemistry of transition metals, but there are lots of systems where both strong correlation and non-covalent interactions are present. Here, this is the pink one, such as metal organic frameworks or active sites of metal enzymes. And I hope also to develop methods that lie at the interface of these two research lines that will be suited for the treatment of these systems where both strong correlation and dispersion interactions are present. Okay, and finally, okay, this area is going to be about surface science. I start doing research also on this. The specific goal of this project will be to transform the applicability of DFT for surface science by using tools that are analogous to ones that I developed for detecting and reducing density-driven errors in molecules. And okay, so this project is a little bit more applied. So as potential collaborators, I would expect to work with SEMES and LCPQ, given that lots of nanoscience and given that what this research line is highly related to both material and nanoscience. So what are when it comes to using DFT in surface science, there are several open challenges. For example, when the standard GG8s are used, one usually obtains very inaccurate barrier heights that are typically underestimated. Another problem, even when so-called specific reaction parameter SRP DFT is used for surface science. One is still not doing well, and this SRP DFT basically uses experimental input. Okay, so recently I helped publishing this paper, and we showed that when it comes to describing barrier heights, the DFT is getting worse and worse as soon as there is more electron transfer involved between the molecule and the surface it is attached to. So for example, when O2 is applied, when O2 is attached to aluminum, there is lots of charge transfer present, and DFT basically standard DFT basically fails in describing this process. On the other hand, when there is very little electron transferred from a surface to the molecule, such as what we have on the right-hand side, platinum and methane, in that case, DFT is doing really well. So basically here in general, failures of DFT when applied to barrier heights of molecules attached to surfaces can be traced back to the density errors and self-interaction errors. Okay, this was also recently confirmed by Perdue and co-workers, where they showed that once one does account for density errors, one gets much better description of the attachment of a molecule to a surface. Okay, so all these things that problems that are all these causes of the problems in applying DFT to surface science, I work this in the area of molecules, where I showed at the beginning tools for reducing density-driven errors, and I believe that these can be ported to the surface science, and that this can greatly improve the description of barrier heights, of binding energy in surface science in general. And okay, so, and in addition to these three topics, I also wanted to mention this paper that it was just recently published, which enables for quantifying and understanding errors in molecular geometries. Here, together with Kieran Berg, I have developed several ways for detecting errors in molecular geometries, and I believe that this provides a basis for short-term projects that can be used for, say, improved structures, faster geometry optimizations, and in general better understanding of energetic errors due to approximate geometries. Okay, and here I go back to the list of topics that I would like to work on. And with this, I would like to conclude and to thank my collaborators and of course you for your attention.